Okay, so question 6, we have this system. So we are going to let this system, we let the mass drop. Okay, when we let this mass drop, the wheel is going to turn or rotate. Okay, so we can see that there is a change in potential energy. There's a gain in translational as well as rotational kinetic energy. So now we want to find also the angular acceleration of this wheel, the moment of inertia of this wheel, as well as the tension in the string or the chord. Okay, so angular acceleration, we know it's given as A over R. Okay, that's our equation 1. So in this equation, we have one unknown. Okay, we have one unknown here. Then we can use this equation to find our acceleration, to find A, where y is simply the distance, which is 1 meter, and the initial speed in the y direction is 0. Okay, so therefore we have that y equals half at squared. With y being 1, we are going to have 1 equals half at squared. So we know the time also, it's 5 seconds. With this, we can find the acceleration as a equals 2 times 1 over 5 squared, giving us 0.08 meters per second. Per second squared, sorry. Okay, so we have found the acceleration, and it's going to assist us as we try to find the angular acceleration. Okay, so angular acceleration using equation 1 is given as tangential acceleration over the radius, which is A over R. We just found our A as 0.08 over our radius. Therefore, the angular acceleration of this wheel is 1.33 radians per square second. Okay, so the second part, we are finding the moment of inertia of this wheel. So to find the moment of inertia, we're going to use conservation of energy. And we know that when we use this conservation of energy, we have rotational kinetic energy. Okay, we're going to use this. Okay, so the change in potential energy is going to be the total gains in kinetic energy. Okay, so now we have mgh equals half mv squared, which is the translational kinetic energy, plus half I omega squared, which is the rotational kinetic energy. Okay, so also we also take this one right here. We know that v squared can be expressed as omega squared r squared, and therefore we can rewrite this equation. Okay, we can rewrite this equation as mgh equals half omega squared. Okay, so notice here I've already factored out the half omega squared because it's going to be common for the right hand side part. Here we're going to have half omega squared, then in brackets we remain with mr squared plus I. Okay, some mathematics here. Right, so therefore, since we're looking for I, we're going to work out and find an expression for I. Okay, so we have 2 mgh over omega squared equals mr squared plus I, from which we find I equals 2 mgh over omega squared minus mr squared. Okay, so what do we have here? We know what the mass is. Okay, since we're looking for the moment of inertia, the mass of the wheel. G, we know what G is. H, we know what H is. Okay, all these figures are there, I mean the values are there in the question. Here also we know the mass, okay, mr squared. Again, what we don't know here is the omega. Okay, so when I was solving, I started by finding omega in advance, but when you reach this stage now, you need to find omega. Okay, so let's go back here. We know that omega equals v over r. Okay, so we can find v from v equals u plus at, because we know what a is. Okay, from the first part, it's 0.08 meters per square second. We know what u is, it's simply 0. Okay, and we also know what t is. Okay, so if u is 0, we remain with v equals at, which is simply going to be 0.08 multiplied by t. Therefore our v is going to be 0.4 meters per second. Okay, from this v we can now find omega. We know that omega equals v over r, which is 0.4 over 0.06, giving us omega as 6.67 radians per second. So now that we know the value of omega, we come back. Okay, we substitute the value of omega, which is here, okay, squared, and then we substitute all those values in the question. We have 2mgh over omega squared minus mr squared. Okay, so if we work this out, we're going to find the moment of inertia of this wheel as 0.087 kilograms square meters. Okay, so we have also done the second part of the question. So now that we know the moment of inertia, let us now consider the tension in the chord. We remember this system. Okay, it's similar to something that we have solved already. So here we know the tension going up and the weight going downwards, producing a downward acceleration. Therefore, we have T minus mg equals negative ma. Therefore, T equals mg minus ma. T equals m multiplied by g minus a. We know a, we know the mass, so the mass is 0.2 multiplied by g minus a. Okay, we found the value of a. Therefore, the tension in the chord is 1.94 newtons. All right. Okay, so this was straightforward. So again, I emphasize I'm a bit fast with these videos. Okay, because yeah, I don't want them to get too big. Okay, by spending more time explaining. So if you need further clarity, you can always post your questions on Telegram. Yeah, I always say that. Okay, so now what are we finding? We are now going to find oh, this one is done. Okay, we now go to question 7. Okay, so here's question 7. Some time to read. Okay, so again here, this right here is supposed to read 30 degrees, not 300. Okay, so it's supposed to read, a disc is made to roll without slipping up an incline, making 30 degrees with the horizontal. All right, that's the correction. Okay, so we have this disc which is moving with a speed of 2 meters per second at the bottom of the incline. Okay, so it's going up the incline. Now we have to find the height. Okay, so the question is saying how high up the incline will the disc travel before rolling back down again. Okay, so we need to find the height to which this disc will travel before it starts rolling back down. Okay, so here we're using the conservation of energy as we are told in the question. So let's take note that as this disc reaches the top, okay, let's start from the bottom, which is our point A. Okay, so at point A here, what do we have? The disc is rotating. Okay, it's rotating, so it's having some angular speed as well as a linear speed of 2 meters per second. So it has both translational as well as rotational kinetic energy, but it has zero potential energy. Okay, so now as it goes up the incline, when it reaches the maximum height, it's going to attain some potential energy, but at this maximum height it's going to stop. Okay, so just before it starts rolling back down, it will be at rest, so meaning that the total kinetic energies are going to be zero. Okay, so as you can see from here, we are saying at point B, which is the top, the final speed or the final linear speed is equal to the final angular speed, and they are both zero, meaning that the translational kinetic energy is equal to the rotational kinetic energy, which is zero at the top. Okay, so notice also from this diagram, okay, since we are looking for h and we are given the distance, so we are saying that h here equals d sine theta. Okay, we know that. Let's keep that in mind as we are working through this problem. Okay, so conservation of energy here gives that gaining potential energy equals loss in the total kinetic energy. Therefore we have mgh, okay, equals half mv a squared plus half I omega a squared. Okay, so notice here, this is the conservation of energy. I'm getting the potential energy at the top being equal to the kinetic energy at the bottom. Okay, so let this be our equation 1. Also, we know that h equals d sine theta. We also know that the moment of inertia for a disk is mr squared over 2. And we also know that omega squared can be expressed as v squared over r squared. Okay, therefore we substitute this into our equation 1, and we're going to have mgh becomes mg d sine theta equals half mva squared plus half, okay, I omega squared. Okay, hope you're following. So we're saying I is mr squared over 2, and omega squared is going to be v squared over r squared. Okay, so we're simply substituting these. Okay, notice here we have to work with v. Okay, we have to work with v, not omega. Therefore that's why we're changing this omega into an expression in terms of v and r. Okay, because that's what we are given in the question. Okay, we know what v is at the bottom, va. Okay, so now we work this further. We have mg d sine theta equals half mva squared plus, okay, if we work this out in the brackets, we'll have half times that half, we have 1 over 4, Okay, and the r squared and that other one are going to cancel out, remain with mva squared. Okay, we go further and add. Notice the expressions on the right hand side are going to add because they are similar. Therefore we have gd sine theta. Notice the mass also is going to cancel out, so we have gd sine theta equals 3/4 va squared. Okay, from which we can obtain an expression for d, which is the distance, as d equals 3 va squared over 4g sine theta. So this a, notice that is the point at the bottom. Okay, so va is simply the speed at the bottom of the incline. Okay, so from this expression we find the distance as 0.61 meters. Okay, so the distance d here has been found as 0.61 meters. Okay, therefore, since we know that h is d sine theta, with our theta being 30 degrees and our d being 0.61, therefore we find our height as h equals 0.61 sine 30. Therefore, the height is going to be 0.31 meters. Okay, so I hope you are following through here. You can always rewind the video and check through, make sure you're clear. If nothing is making sense here, reach out to my inbox. Okay, so this is where tutorial sheet 7 is ending. I hope to meet you for the next tutorial.